Welcome to my video lecture based on Millman's theorem. In this lecture, we will highlight about a new theorem that is based on Millman's. This topic is included in Electric Circuit Theory paper for PCE 301 and included in the markout syllabus. Myself, Millman, Assistant Professor of Electrical Engineering, Department of University College. In the previous lectures, we have discussed about different theorems like superposition, Thevenin's, Norton's, and also we have discussed about maximum power transfer theorem. Based on this theorem, different network problems can be solved in easier way. For that reason, this theorem has been developed. Millman's theorem is basically based on a simple concept that is using source transformation or voltage source and current source combination. In that way, this theorem has been developed, and the basic laws of like Kirchhoff's law, voltage law, current law, and Ohm's law is also very important for understanding all these concepts. So today in this lecture, we will start with Millman's theorem. Let us consider a number of admittance y1, y2, y3 up to yn are connected together at a common point S. Here we have shown that y1, y2 up to yn, it is connected together with a common point S. If the voltages of these three ends of the admittance with respect to a common reference n are known to be V1n, V2n, V3n up to Vnn, then Millman's theorem gives us the voltage of the common point S with respect to the reference n. And we can calculate that as follows. By applying Kirchhoff's current law in the node S, we are getting that summation of current IP equals to 0. That means IP equals to Yp bracket Vpn minus Vsn. Or from calculating this one, we are getting that Vsn equals to summation of P equals to 1 to n Yp Vpn divided by summation of Pn 1 to n Yp. That means gives us the value of the voltage at node S. Basically, this theorem is an extension of Kirchhoff's current law. In Kirchhoff's current law, we know that summation of currents looking at a node equals to 0. From this concept, this theorem has been developed, and the voltage at the point S for a node of n we can calculate easily by applying the Millman's theorem. Now let us consider the statement. This theorem states that if the several ideal voltage sources V1, V2, V3 like that in series with the impedance of Z1, Z2 up to Zn are connected in parallel, then the circuit may be replaced by a single ideal voltage source V in series with an impedance of Z. What is that? Suppose we have voltage sources like V1, V2 up to Vn, and those voltage sources are connected with some impedances in series like Z1, Z2, Zn. Then we know the concept that when voltage sources are connected in parallel, they can be sum up like V1 plus V2 plus V3 in that way. But here the fact is our internal impedance of Z1, Z2, Zn are also connected. So, for calculating this value of V, we have to take the concept of Millman's theorem, which is summation of Vi Yi up to 1 to n divided by summation of Yi where I equals to 1 to n. So, from this easy calculation, we can calculate the value of voltage, which we can put it in a single form. So parallel connected voltage now becomes a single voltage of V. In similar way, we can calculate the Z also, where Z is 1 by summation of yi, where I equals to 1 to n. So, in that way, we have just calculated the value of voltage V and calculated the value of Z and just make it a simple circuit which consists of a voltage source with a series impedance of Z. So that is the concept of Millman's theorem. Secondly, if the several ideal sources, current sources, I1, I2, I3 like that connected in parallel, if impedance Z1, Z2, Z3 are connected in series, they may be also replaced by a single ideal current source I in parallel with an impedance Z. Just the reverse of our voltage source with series resistance. Here, if current sources are placed with parallel impedance Z multiple times, like I1, I2 are placed with parallel of Z1, Z2 up to IN, then we can put this total network into a simple network of consisting of one current source with a parallel one impedance. How? Again the Millman's theorem will become our picture, and that is I equals to summation of II divided by yi, where I is 1 to n, whole divided by summation of 1 by yi when I is 1 to n. In that way, we can calculate the value of the single current source from all the current source present in the network. And we can also calculate the value of admittance y by the same way, that is 1 by yi, where I is 1 to n. Or we can also write z in place of y, that is z equals to summation of zi, where I equals to 1 to n. In that way, we can also make a simple current source with parallel resistance or parallel admittance or parallel impedance by using Millman's theorem. Now let us prove the theorem. So let us consider, using superposition theorem, the short circuit current through AB, considering one source acting alone and replacing all other sources by its internal impedance. The short circuit ideal voltage source is definitely ISC equals to V into YI and ISC2 equals to V2 into Y2. In that way, ISCN equals to VNYN. So total short circuit current through AB equals to ISC1, ISC2 plus ISCN. So in that way, we can write that the short circuit current is summation of Y to Y equals to I1 to N, that is VI, YI. And similar way, we can calculate the impedance also when all sources are removed, and it will be 1 by Y1 plus Y2 up to YN, that is 1 by summation of I equals to 1 to N YI. Thus, from Millman's theorem, the equivalent voltage is ISC into Z, that is equals to summation of Y equals to 1 to N VI YI divided by summation of Y equals to 1 to N YI. From the equation 5.8 to 5.9 and 5.10, the Millman's theorem is proved. So, 19.3.2, using superposition theorem, the short circuit current through AB considering only one source acting alone and replacing all other sources by its internal impedance. So, ISC equals to definitely I1 into Z1 divided by summation of I equals to 1 to N Zi. Similar way, ISC2 equals to I to Z2 divided by summation of I equals to 1 to N Zi. In that way, we can calculate the short circuit current using superposition theorem, where all the other sources are replaced in this given circuit, or for previous one in this circuit. Okay. So similarly, we will calculate the short circuit current by sum of all these currents ISC1, ISC2 up to ISCN, and then we can find the amount of current by using summation of I equals to 1 to n I1 j I divided by summation of I equals to 1 to n zi. Impedance is looking back from A to B with all sources removed, that is equals to z equals to summation of I equals to 1 to n zi. From all this equation, the Millman's theorem is proved. Now let us consider one simple example of Millman's theorem. So find the load current using Millman's theorem, where all the given values are in ohm. So we can see that there are 3 voltage sources, 1 volt, 2 volt and 3 volt, and all these voltage sources are connected with series resistance of 1 ohm, 2 ohm and 3 ohm. Now we will just change those resistance values in admittance. That means we have to divide those things 1 by 1 or 1 by 2 or 1 by 3. Definitely, if we want to convert those in admittance, then that means that will be reciprocal of resistance. So we are getting the values of Y1, that is 1 ohm, 1 mho, Y2 that is 0.5 mho, and Y3 equals to 1 by 3 mho. And these will be all in ohms, not in mho. These will be all in ohms. By Millman's theorem, the equivalent circuit is now shown. This one. So we are just putting those values, that is Vi into Yi, summation of Vi into Yi divided by summation of Yi. So here the value of V is Y1. So we have put it V equals to 1. Value of Y1 equals to 1. So V1 Y1, that is 1 into 1. Next value of V2 is 2 and value of Y2 is 0.5. So it is 2 into 0.5. Thirdly, V3 equals to 3 and the Y3 value is 1 by 3. So all these values we have just sum up for getting the summation of Vi Yi. Similarly, we have divided this value with summation of Yi, and Yi values are 1, 1 by 2 and 1 by 3. So we have just sum of those things and we have got the value of V. This is basically the value of V. Now we have to calculate the Z, total Z, which will be definitely summation of 1 by Yi. So here we will sum up 1 divided by 1 plus 1 by 2 plus 1 by 3, that means this value. We will get 1 by 11.6, that means 6 by 11. So that is the Z value we are getting. So from there we can easily calculate the value of current. So definitely this will be, we can convert this circuit to a simple circuit now, that will consist of voltage source, which value we have calculated as 18 by 11 with a series resistance which value is 6 by 11 and it will be connected with this load resistance 10. So now the circuit becomes like this. So we can easily calculate the current, and current will be V divided by R. R1 plus R2 was Z1 plus Z2. So here the value of V, that is 18 by 11, divided by R1 plus R2, that is Z1 by Z2, that is 6 by 11 plus 10. This one I have written. So we are getting the current through 10 ohm resistor is 9 by 58. So in that way we can calculate the value of current using Millman's theorem, and the circuit becomes so simple and we can easily calculate from it. So you can practice different problems like Millman's theorem, and this theorem is also helpful for simplifying any circuit. But you have to consider or remember in mind, this theorem will be only applicable when voltage sources are connected with series resistance or series impedances. Several voltage sources will be connected with several impedances in series, or several current sources with parallel impedances connected in a network. That can be also simplified by Millman's theorem. Otherwise, if the voltage source is present, resistance is put in parallel, definitely we cannot apply Millman's theorem. Or current source is there or resistance connected in series, there we also cannot apply Millman's theorem. Only the two conditions where we can apply, where voltage source is placed and resistance or impedance are connected in series with that voltage source, and there will be several voltage sources and series resistance are present. And similarly for current source, where where more than one current source with parallel resistance or impedance are present, there we can apply Millman's theorem. For reference book, you can go through the book of Abhijit Chakraborty of circuit theory, and you can also go through the books of different books of circuit theory like 50 raised to the 5, or you can also go through the book of Samudjit Ghosh. Like different books are there, but I will prefer a Chakraborty book of circuit theory, where different problems related to network analysis has been solved. In my next lecture, I will discuss about reciprocity theorem and several problems related to that. Those we will solve here, and that will be our last topic based on network analysis. So thank you all for listening.